Hi and good day, Dr. Chan. This is Sundus and I'm going to be doing the introduction. So mechanics of materials is a field that refers to several methods of analyzing and calculating stresses and strains in structural members under various types of loads. Knowing these pressures and tensions helps in several things, the most important of which is the design of safe structures that can support the loads. Also, the study of the mechanics of materials is useful in calculating stresses and strains in members such as columns and nails. The strength lies in the mechanics of materials being the ability of the structure to withstand the relevant load without creating plastic deformation. And in this assignment, our group has chosen the climbing walker as an example to demonstrate and solve problems with the four learning outcomes of the course. In this assignment, we will study the climbing walker when it's under the action of axial and torsional loads. Axial loading is defined as applying a force on a structure directly along the axis of the structure. On the other hand, torsional loading is defined as the loads that imparts the turning moment of the torque.
Now I will present the dimensions of the climbing walker. So the climbing walker is composed of different paths of shaft such as AC, AB, EF, and ED. So the assumption we made for the climbing walker is that height is adjustable and the weight is 2.2 kg. The maximum weight can support 120 kg. The diameter of shaft equals to 0.03 meter. So the climbing walker is made up of high-strength material that is stainless steel and aluminium alloy. Young modulus for stainless steel is E equals to 190 gigapascal. The climbing walker is ergonomically designed handle with soft brownie contour grip. LO1 soft probes involving a body under the action of axial and torsional load. In this case, shaft AC is evaluated. Firstly, FPD of the shaft AC was drawn, and then all the external forces occurring at the shaft were labeled. Thirdly, the mass of the test subject is calculated. For the axial loading, forces acting on the shaft is calculated, that is, weight is calculated by using the formula W equals to mg. Normal stress is calculated by using the formula stress equals to pressure over area. So we can get the area by using the formula A equals to pi d squared over 4. For the part of torsional loading, shearing stress is calculated by using the formula torque equals to T multiplied with C over J. LO2 soft probes involving stress in beams. In this case, shaft EF is evaluated. Firstly, axial stress of the shaft, shearing stress of the bow, and bearing stress of the beam shaft are calculated by using the formula stress equals to pressure over area. Secondly, bending moment at point E is calculated by using the formula M equals to FD. D is perpendicular distance from the pivot. And thirdly, the moment of inertia of the shaft is calculated by using the formula I equals to 1 over 12 pi r fourth. Last but not least, maximum bending stress in the shaft is calculated by using the formula stress equals to mc over I. That is, m is obtained from step 2 and the I, moment of inertia, is obtained from step 3. For LO3, we evaluate stress and deformation of biomedical devices due to compound load. In this case, bilateral sides of the climbing walker ABCD is evaluated. Firstly, free body diagram is drawn and the forces acting on the component are calculated. Secondly, normal stress of supporting rod AC and BD is calculated by using the formula stress equals to pressure over area. Thirdly, deformation of the supporting rod AC and BD is calculated by using the formula delta equals to PL over AE. So there are alternative approach that we can get the deformation. So the strength is calculated by using the formula strength equals to stress over Young modulus, and then the deformation can be obtained by using the formula strength equals to change in length multiplied with original length.
Hi, I'm Jael and I'm going to discuss about the result of LO1. For LO1, we want to solve problem involving a body under the action of axial and torsional load. So we take the AC shaft to evaluate the axial and torsional loading on it. This is the free body diagram of AC shaft. We make assumption that the weight of the patient is 637.65 Newton. Since the climbing walker has 4 legs, so we divide the force by 4. The force applied on the shaft AC is 159.41 Newton. To determine the normal stress on the AC shaft of the climbing walker under axial loading, we should first compute the area of the AC shaft. Formula of area is pi d squared over 4. D is the diameter of the shaft, which is 0.03 meter. Then we get the area of the shaft is 7.069 10 power of negative 4 meter squared. Hence, the normal stress acting on AC shaft under axial loading is 225.51 kPa. For torsion loading, assume the torsion is 1000 Nm. To compute the shearing stress applied on the AC shaft, we should first calculate the polar moment of inertia J by using the formula pi d power of 4 over 32. The radius of the shaft C is calculated as 0.015 meter, so the polar moment of inertia is calculated as 7.952 to 10 power of negative 8 meter power 4. Thus, the shearing stress acting on the AC shaft under torsional loading is 188.63 megapascal. Next, I will pass the presentation to Timothy to present about the result of LO2 and LO3.
Hi, I'm Timothy. So moving on to the next level, which is to solve problems involving stress in beams. So in this section, we have chosen to focus on the force acting on the shaft EF that connects to the bilateral sides of the climbing walker. So as you can see, this figure for the connection to the bilateral sides through this double shear bolt connection. So when the patient is applying load to climbing walker, there will be an outward force that is transmitted from the body weight to the supporting hand and then onto the climbing walker. So we assume that the force applied by each of the hands of patient is 300 Newton that pass through the bolt connection. So first we will calculate the axial stress of the beam, which is the shaft EF using the formula force over cross-section area of beam. The axial force is F sin 10, and the cross-section area is pi r squared, with the radius of the shaft being 0.03 divided by 2. Then here we got the axial stress to be 73.7 kPa. So moving on to the shearing stress on board. Shear force applied is F sin 10, same as the previous formula. However, the shearing area contact have to be multiplied by 2 because of the double shear bolt connection. The final answer for the shearing stress will be 137.4 kPa. So moving on to the bearing stress, the formula is the force exerted divided by the multiplication of bolt thickness and also for the bolt diameter. So the thickness of the bolt is same with the diameter of the shaft, and then we will get the answer is equals to 115.77 kPa. Lastly, for this LO, we'll be calculating the maximum bending stress in the shaft EF. So to do so, we will first have to calculate the bending moment at point E, which is the perpendicular distance multiplied to the force exerted, and equals to 147.72 Nm. Then, to get the moment of inertia of shaft EF, the formula for the cylindrical rod EF is equals to 1 over 12 pi r power to 4. So after calculating the centroid of the shaft EF, which is the center point of the shaft, which equals to the radius of the shaft 0.015, the maximum bending stress calculated and is 16.7 kPa. Moving on to the next LO3, which is to evaluate stress and deformation of biomedical device due to compound load. In this session, we'll be focusing on to the bilateral sides of the climbing walker as shown in figure 5A, B, C, D. And then first to get the force acting on the rope AC and BD, which is FA and FB. To get the FA and FB, we have to use the static equilibrium equation, which is equal to the summation of force component on the XY axis. Okay, this is the equation, and make it equals to 0, and then we'll get the FA equals to FB. Now with the FA and FB, the normal stress and deformations of the rod SC and BD can be calculated using the formula force over cross-section area of the rod. Here we got the formula. Here we got the normal stress of rod AC equals to 245.66 kPa. It's lower than the supporting rod BD with 283.86 kPa. For the deformation, we will be using the formula PL divided by AE, where P is the FA and FB respectively, and L is the length of the rod, with A is the cross-section of the rod and E is the Young modulus of stainless steel we assume, which is 190 GPa. So from calculation, the deformation is equals to 0.97 micrometer and 2.205 micrometer respectively for the two rods AC and BD. Here I will share another method for calculating the deformation. This equation, we have to calculate the stress and then the strain of the rod first before we can get the length of deformation. As you can see, the results here are the same with the deformation of 0.97 micrometer and 2.205 micrometer for rod AC and BD respectively. Thank you.
Our group has chosen two-wheel climbing walker as the biomedical device in this assignment. It is because we can clearly observe the effects of axial and torsion loading on the body and study the stress and strain acting on the walker due to the applied load. We can also easily measure and determine the parameters used in the experiment, such as mass, length, height, elastic modulus, and more. For axial loading, we calculated the resultant forces and drew a free body diagram to visualize the different components of forces acting on the walker's shaft. For torsion loading, we calculated the internal torque acting at a specific location of the walker's shaft. Stresses and strains acting on different components such as bolts of the walker are also calculated. Before proceeding to the calculation part, we have measured and determined the basic parameters that will be used in the calculation. For example, length, height, diameter, and also Young modulus. Young modulus is also known as elastic modulus, which is the measure of the rigidity or stiffness of a material against deformation when the force is applied lengthwise. It can be determined by using the formula elastic modulus equal to change in stress divided by change in strain. Change in stress and strain can be determined from the gradient of elastic region of the stress-strain curve. In elastic region, material obeys Hooke's law, which states that the stress applied is directly proportional to the strain experienced by the material. Material can restore to its original dimension when the stress is removed. There are some improvements can be made for the worker. By referring to the formula stress equal to force divided by area, we can minimize the stress in the worker's shaft by increasing the cross-sectional area of the shaft when the force applied is constant. By referring to the formula strain equal to stress divided by elastic modulus, we can minimize the strain and deformation experienced in the worker's shaft by increasing the elastic modulus when stress applied is constant. We need to design the worker with suitable parameters such as length and diameter and select the most suitable material so that it can function well at optimal cost. Other factors are also important such as material strength, ductility, and fatigue resistance. Ergonomically, design handle with soft vinyl, contour grip, and rubber tips and legs can be added to improve overall comfort and also the function.
So in conclusion, applying real-life examples such as the climbing walker helps to understand the concept of mechanics of materials in our daily life. And by using the climbing walker as a real-life example, we were able to understand and apply the learning outcomes of this course and also solve problems on the axial and torsional loads as well as stresses in beams were calculated. We have also learned the improvements that could be made on the climbing walker to give the patient a better experience. That's it for our group. Thank you for listening.